I welcome all of you to the 74th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, Trichy, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Dr. S. Balakrishnan from Vellore Institute of Technology, or popularly known as VIT Vellore. Dr. Balakrishnan obtained his PhD at National Institute of Technology, or NIT, Tiruchirappalli, Tamil Nadu in the year 2012. Followed by this, he carried out postdoctoral studies at Center for Nonlinear Dynamics, Bharathidasan University, Tiruchirappalli for an year. He then joined as a lecturer at Vellore Institute of Technology in the year 2013. Dr. Balakrishnan's research interests cover quantum computation, quantum communication, quantum game theory, and foundations of quantum mechanics. He has published a large number of papers in the reputed journals and contributed to several conference proceedings. He has guided postgraduate students in physics and undergraduate students in engineering for their research work. At present, he has been guiding 5 research scholars towards their PhD degree. Dr. Balakrishnan has been involved in teaching the courses Classical Mechanics and Quantum Mechanics for the MSc Physics students since the inception of MSc Physics program at the Department of Physics, VIT. He has been in several administrative committees as well. With this short introduction, now I invite Dr. Balakrishnan to deliver his lecture. Over to you, Dr. Balakrishnan.
Right, sir. Thanks a lot. First and foremost, I thanks for giving me the opportunity to present in a very nice forum. Of course, I have a long-standing association with Bharathidasan University. As Sir pointed out, I have been associated with Bharathidasan University since my PhD time. Professor M. Lakshmanan, he was my doctoral committee member. So since that time, he knows my work. And after my PhD, as soon as I submitted my thesis, I joined his group, and I was there for 1 year. And of course, I know Professor Senthilvelan sir also. Right. And before I start, perhaps this disclaimer is very much necessary. Though the lecture series on nonlinear dynamics, I'm a bit scared to deliver my talk here because basically I'm from quantum computation and quantum information researcher. And considering the audience and the topic slightly deviating from the mainstream of this forum, I wish to take you to a new direction, which perhaps will give you kind of impression, and you will have a look at it in the future. Right. With this few words, introduction and disclaimer. So it is kind of more of a general talk. Wherever possible, I will touch upon the technicality, and towards the end, we can have a discussion. So that is the aim of this talk. So with this brief word, let me share my screen. Right. So I will also write something. That's why I wish to have this. Right. I hope you can see the screen. Sendhilan sir, can you see the screen?
Yes.
Right. Right. Fine. So the title of my talk is something like this: no-go theorems. Right. Basically, we have a quantum computation. Basically, we use the rules of quantum mechanics to pursue the computation process with higher speed. That is the very intention. But the traditional classical computer has the very fundamental process known as cut, copy, and paste. So these 3 actions are very much inevitable in our classical computer. But towards the end of this lecture, you will realize that all these 3 processes are not at all feasible if you have a quantum computer. So in a quantum computer, it's not possible to cut, it is not possible to copy, it is not possible to paste. So what? So then why we have to have a quantum computer, right? That's a different question altogether. But let us try to understand the nature. Still, it is very incomplete, very intriguing, and we will see how much we have reached and what are things to be done to understand the very fundamental nature of microscopic world. Right. And before I start, I can justify why I'm supposed to be here. At least this year, Nobel Prize is given for these three gentlemen, Alan Aspect, Closure, and Zellinger, for the experimental verification of Bell's inequalities. So, quantum entanglement is the very intriguing property, weird nature of microscopic world, and that is being tested and that is being suspected by our own person, interesting scientist, namely Einstein. And he published a paper known as EPR, Einstein Podolsky Rosen, and in the year 1935 in Physical Review. So that was a path-breaking work, and Einstein was saying that quantum mechanics was not complete to understand the nature, and hence he come up with the new notion that there must exist a hidden variable, include that hidden variable, thereby you can complete the so-called quantum mechanics. And nearly after 30 years, we have John Bell, who proposed the very test bed known as now Bell's inequalities, which helped the scientists to understand the nature of microscopic world. And using Bell's inequalities, these three gentlemen, Aspect, Lawser, and Zellinger, performed very, very nice experiments, and they proved that Einstein was wrong and quantum mechanics indeed it's correct. And of course, now we have variants of Bell's inequalities, and all of them are being tested even now, and we don't find any sort of violation. And we understand that quantum mechanics is indeed complete in the sense that it can capture the nature. And what is I'm going to talk about, as my title of the talk says, we are going to find out there are certain things which are not possible in the basic quantum computation, and they are known as no-go theorem. And no-go theorem, that is what the very general word. What are the actions or the operations are not possible in the purview of quantum mechanics? We are going to see, and we are going to understand, and what is the cause of it, what is the consequence of it, and where the road will take us to. So the road will take us to so-called the new notion known as law of conservation of quantum information theory. Right. It is at the very infant stage. Okay, that I must agree that it is at the very infant stage of this proposal, but still there are big shots in the field who predict that there must be a conservation law with respect to quantum information theory as well. So in order to appreciate this, we know the conservation law, right? Conservation of law of energy. So similarly, we should have, or we must have, a conservation of quantum information theory as well.
Balakrishnan, is it law of conservation of quantum information or law of conservation of quantum information theory?
No, it's supposed to be conservation of quantum information. It is conservation of quantum information. Yes. So we are going to see that point towards the end, and a lot of things to be done. And basically, the presentation is going to be based on three major papers, and one is from the paper from Professor Pati's group, and it is published in PRA. And the rest of the content, what I'm going to present, is from my PhD student who works on this notion known as deleting machine. In fact, this leads to the notion known as no-deletion. So we are going to see the no-go theorem from the starting from the very basics, known as so-called cloning and deletion. Then we will proceed to the further thing. And towards the end, I will also indicate the conservation of quantum information and what are the open questions exist in the field. And right now, what is our understanding? That is the ultimate point. And still a lot of debate is going on why we have to consider conservation of quantum information. Right. So with this brief note, let me get into the basic notion. Right. What do you mean by no-go theorem? So the operations which are impossible to achieve in the description of quantum mechanics are in general stated as no-go theorem. And there are a very well-known famous no-go theorems are available. And of course, there are few more in the list. I have mentioned only these 5. And of course, there are few more. So the first and foremost interesting no-go theorem is no cloning. So it means we cannot copy a quantum state, which I will describe in the later slides. And another no-go theorem comes in the name of no deletion. So we cannot also impossible to delete a state, unknown state, of course. And no partial erasure, no broadcasting, no flipping, and so on and so forth. Right now, in this talk, we confine our attention on no cloning and no deletion. And why we need to study these two, you will understand as we proceed further. Right. So the no cloning theorem. So when I say cloning, it is nothing but copying a process. Okay. So general, this is the table I expect. So I have two inputs. So A, 0 and 0. So output is expected to be 0. So I need to have an operation such a way that the input is copied. Input is copied. That is what I want. Of course, we do have certain operations. Let me write down those operations. It comes in the name of controlled NOT. So in the classical computation, we know the NOT operation. So in a similar way, we have an operation known as controlled NOT, shortly C0. So basically, C0 operation is something like this. So let me write down the most general 2-qubit state. So A get 0, 0 plus B get 0, 1 plus C get 1, 0 plus D get 1, 1. Right. And of course, A, B, C, D can be a complex number, and they're supposed to obey the normalization rule. So mod A square plus mod B square mod C square plus mod D square should be equal to 1. And this is nothing but the 2-qubit system. And the very action of C0 is something like this. So this is the first qubit, and this is the second qubit. So whenever the first qubit is in the 0 state, whenever the first qubit is in the 0 state, the second qubit is also known as target qubit, which is left as such. So if it is 0 means it is 0. So if it is 1 means it is 1. So whenever the first qubit is 0, the second qubit, namely the target qubit, is left as such. On the other hand, when the first qubit is 1, then it flips the target qubit. If it is 0 means it becomes 1. And if it is 1, then it becomes 0. So this is the basic operation of controlled NOT. Of course, one can write down the matrix form as well. So what does this? What is the action of C0? Very simple. So when I have C0 acting on a state something like 0, 0, it will give me 0, 0 only. So when C0 acting on 0, 1, it will give me 0, 1 only. And when it acts on 1, 0, then it becomes 1, 1. Right. This is what essentially I'm copying, right? So 0, this second qubit, it was 0, but now after the action of C0 becomes 1. So it is copied, right? So same is the case with the state 1, 1. So it becomes 1, 0, right? So here you can see that 1, 0, when C0 is acted upon, then it becomes 1, 0. So essentially, it looks like I am copying, right? But the point is C0 can do only under this case because we know the state. But when we have an unknown state, it is not possible. When we have an unknown quantum state, it is not possible. Why it is so? Why we cannot copy an unknown state? Because the linearity. So the linearity principle of quantum mechanics prevents us from copying the state, right? So that is what is written over here. So I have a state phi which acts on B. I should have an unitary operator such a way that I should copy it in the second qubit. So the get B becomes get 0 or get phi rather. So same is the case here. So it's supposed to be, let me write on psi, and it is supposed to be psi. But what happens here, due to the linearity, it is not. Okay, let me explain this point a little more clarity. So what I have, let me say the most general state like A0 plus B1. So basically a 1-qubit state. So 1-qubit state, and this is the blank state. It is something like, see, when you want to take a photocopy, you should have a blank sheet, right? White sheet upon which the content is being copied. So same thing we have here, the blank sheet, and upon which I want to copy. So after the process, after the application of the unitary operator, I'm supposed to get get psi, get psi. So if I apply this, what is the rule? What I am getting here? So A0 plus B1 and A0 plus B1. Of course, the tensor product is assumed over here. So we have A square 0, 0 plus B, A into B 1, 0 plus B into A 0, 1, and finally we have B square 1, 1. But what we are supposed to expect when we have a C0 operation, so C0 is acting on the state A get 0 plus B get 1 on a blank sheet. This is the blank sheet, right? So what I am getting here, I am getting something like A 0, 0 plus B 1, 0. So this is what, in fact, 1, 1, sorry, 1, 1. So this is what we are getting by so-called the C0. It looks like a copy. So I'm having this. Okay, so 1 becomes 0 becomes 1. So it looks like copied. But the actual unknown state, this is the unknown state. If I do the copying process, I'll be landing on this. So if you compare these two, you can see the fact that AB supposed to be equal to 0. AB supposed to equal to 0. Then only it is possible. So what does it mean? Either A has to be 0 or B has to be 0. So if A is 0, then you collapse to the known state. Or B is 0, it collapses to known state. So this aspect is nothing but the no cloning. Because of no cloning, we have a very, very strange thing. Okay, if we cannot copy, then what is the advantage? Why? So the very fundamental action of copying is not used. So is it a restriction or a constraint in the case of quantum computation? The answer is no, because scientists look at this thing in a different way. Because when you have two parties, let us say Alice and Bob, and they are communicating each other, sending the qubit. And now what happens? There is an Eve who is trying to intercept. And what happens, since the state what is being transmitted by Alice to Bob, it is not known to Eve, and so Eve cannot copy. So Eve cannot copy the unknown state, because of which it is always advantageous to have a no cloning process. So though it looks no cloning is a very fundamental restriction, but it is not so. In a very positive side, during the communication process, quantum communication process, we can exploit the no cloning aspect, because of which the interceptor cannot copy the unknown state and transmit the duplicate state. So no cloning, this is how people understand and appreciate the significance. And similarly, we have another aspect known as no splitting. So if I have a quantum state which has something like this, cos theta get 0 plus e to the power I5 sine theta and 1. So basically it has this ket psi has a dependency on phi and theta. And is there any operation which can help me to write something like one parameter depends and another, let me say chi b, right? So is it possible to split the dependency of the parameter? So theta and phi, so that two entity of a qubit. So one single qubit has the information contained in theta and phi. And is it possible to have a process such a way that we can have theta and phi can be separated out? So this is known as no splitting. So no splitting also is impossible in the domain of quantum mechanics. So similarly, no partial array. So meaning to say, so if I'm able to split, I can delete one of them. I can erase one of the parameter. So which is not possible. So symbolically, it is represented here. So you have your qubit, and this is something like a blank state. And what is not possible, I cannot copy this state to here. That's why this arrow is given, which is not possible. Similarly, if I have two copies, Can I delete one of them? So it is not possible. So deletion is also not possible, which we will discuss in detail as we proceed further. So this is the cloning and deletion. By the very definition, we get the impression that cloning and deletion are a reverse process of each other. Cloning is the reverse of deletion and deletion is reverse of cloning. We get such an impression, but fundamentally it is not. It is not. Cloning is not a reverse process of deletion, and the deletion is not in a reverse process of cloning. Still, this is an open question. If you tell that, then what is the reverse process of deletion? That is an open question. What is the reverse process of cloning? That's the open question. Right. So this is one aspect, and the other aspect is having one single qubit containing two information. Can I split into two? That is also ruled out, which says the no splitting. So the qubit containing information cannot be disintegrate, cannot separated by means of two different states. And if I want to merge them, that is also not possible. That is also not possible. So the reverse. So all this process gives us the very interesting notion why it is fundamentally not possible to pursue certain operations. And we do have a very strong reason. One is the principle of linearity. The other one important aspect is unitary nature. These two are the very fundamental aspect of quantum mechanics, which indeed prevents the cloning and the deletion. And interesting to mention, we don't know what are the inverse operation of these two, right? And let me get into the notion of no deletion. So what is no deletion? Given a two copies of unknown quantum state, it is not possible to delete information in one of which. So I have a state something like this, get phi, and I want to have an unitary operation, which I call it as deleting mission. So do I have a deleting mission such a way it can delete one of the copies? So the answer to this question is it is not possible. So it is not possible to delete deterministically, but it is always possible to have a probabilistic deleting mission. So now at least we can do probabilistic cloning and probabilistic deleting. So which is possible, and there are plenty of work in this direction. Is there any way one can improve the probability of cloning or the deleting? So all these questions are being addressed very nice way. And the very first fundamental deleting mission was given by Patti and Bronstein, and it is celebratively known as Patti-Bronstein deleting mission. This is kind of a base and the starting point for any research on no-go theorem. Right. So let me explain the operation over here so that we can understand and appreciate the significance of it. Okay. So we have the two qubits orthogonal states, and this is A is nothing but something like the mission state. So this is nothing but a mission state. And what we are trying to do is whenever the mission sees the two copies, identical copies, it will delete the second one. So here you can see ket 0 becomes ket sigma. And it's then the mission state is also changed. The mission state is also changed. So here you can see 1 becomes sigma once again. Whereas nothing happened in this case because the mission sees two different input state, it left the qubits as such. So there is no action of the operation when the input qubits are different. Whenever the mission sees the two identical copies, it will try to delete the second one. And of course, we impose all the orthogonality rule as per the norms of quantum mechanics. We proceed further. But very important aspect is of any deleting mission, for that matter, the very action of deletion affects so-called the original state as well. So here the definition comes for the orthogonal state, but when you perform the deleting operation for a most general single qubit, what will happen? The deletion process affects the original state as well. So we are not able to retain the so-called the first qubit in its original state. So the action of deletion affects the qubit which we want to retain, and also the second qubit is not perfectly deleted. It is not perfectly deleted. We can delete only in a probabilistic way. So what is the problem? What is the maximum probability we are getting? That one can compute using the quantity known as fidelity, which will come to in the next slide. Right. Then we propose a new deleting machine, which is in fact the reverse of Pati-Bronstein. So Pati-Bronstein deleting machine works whenever the machine sees two identical copies, it deletes the second qubit. Here we come up with a different deleting machine, such a way that whenever the machine sees different input qubits, then it will delete the second one. So this is exactly the reverse operation of Pati-Bronstein, and with this we started our analysis. You'll be wondering why it has to, but our intention is something like this. Do we have any equivalent of Pati-Bronstein? That's why we come up with a very contradictory operational definition of deleting machine. So when the deleting machine sees two different input states, then it deletes the second qubit, and whenever it sees the identical copies, it retains, it sends the qubit as such. So this is the operational definition, and of course all the quantum mechanical rules are being held here also. So considering that, we analyze the aspect and we come up with the calculation. First thing is fidelity of retention. So what is fidelity of retention? So as I pointed out, the very action of deletion affects the input qubit as well, affects the input qubit. So the qubit which we want to retain and which we want to delete, there are two things. So when we try to delete the second qubit, retaining the first qubit, that is becomes impossible. So the input qubit is also being affected. So we want to understand how much it is being affected. So that can be measured by calculating the fidelity of retention by the very definition. So FR equal to, it's basically the inner product of psi with ρ1, and psi is the initial state, ρ1 is the reduced density matrix, and we can get into the expression. And we, of course, we use the notion mod alpha square mod beta square equal to 1. We translate beta into alpha, we got into this expression. And similarly, one can also define fidelity of deletion by seeing how much the second qubit is being deleted in comparison with the input state. And when we do so, we get this expression. So these two expressions, fidelity of retention and fidelity of deletion, gives an indicator. It's an indicator of the performance of our deleting machine. And of course, this is also being calculated. This is for so-called Pati-Bronstein. Of course, we can also perform the calculation for our deleting machine. And this is the graph looks like. So the retention fidelity, you can see the graph here. When alpha is 0, so along x-axis we have the input parameter, namely alpha, and along y-axis we have the retention fidelity. Of course, it ranges from 0 to 1. And when alpha is 0, basically what we have, the input state is nothing but 1. So we have the known state. So known state can be deleted perfectly. That's why there is no issue here. And when alpha becomes 1, we have get 0. So that's why we got into this expression. And during the superposition state, when you have a superposition state, you got the expression something like this. So the graph is monotonic function, and it's very interesting to see the characteristic at the equilibrium, superposition state. So this state is important. Most of the times we compare the situation with the superposition state, and we can make a proper analysis, because alpha 0, alpha 1, it is something like, the known state, and hence it will not bring anything new. That's why we always compare the superposition state. So this is with respect to the retention fidelity, and the similar sort of a graph we obtained for deletion fidelity. You can see the we can see the lowest value here. So the lowest value is something like 0.5, and in this case we have something like 0.75, which of course analytically one can also find out using the expression, right? So yes, sir.
Excuse me. There is a question in the chat box. You want to answer now, or you want to take it at the end of the talk?
Yeah, please, sir. Please go ahead. Yes. Yeah, we can have the question.
Can you read the question in the chat box?
Sure.
A student has asked, can you please explain about reduced density matrix?
1 minute, sir. Yes, let me take it. Yeah, Preeti has a question. Can you please explain about reduced density matrix? Yes, okay, sure. Right, so let me write down here reduced density matrix. The most general state is something like this, as I mentioned here earlier. So we have a 2-qubit system, and we are writing the most general state, something like this. And for the sake of understanding, let me use the notation capital A and B. So what we have, I have a qubit, let us say single qubit. So A1 get 0 plus B1 get 1. And they are supposed to satisfy the condition mod A1 square plus mod B1 square equal to 1. Similarly, I consider another qubit A2 0 plus B2 1. Right. So what is the most general state I can write down? The most general state is something like the so-called the tensor product I should write. Right. So if you do so, you can get into this expression. This is a 2-qubit system. Right. Now, what I want to do, I want to find out the mixture, right? Basically, we want to have density matrix, and it is also called density operator. Basically, it is a misnomer. Please don't confuse, because usually we reserve the word operator for the operation, right? Not for a state, but conventionally it is called a density matrix or density operator. So how do you define density operator? By finding out the outer product. So this is known as outer product, right? When you calculate an inner product of a quantum state, you will get a number, and when you take an outer product, you will basically get a operator matrix form, right? What I want to find out, so this is the state, this is the density matrix of the entire state, rho AB. But what I want to get rid of one of the subsystem. Okay, B, let me call capital B is what I want to get rid of. So what I will do, I will trace out B. I will trace out B from rho AB. By doing so, I can find out rho A. And similarly, we can find out rho B by tracing out rho A from the overall composite state. So this is how we find out the so-called density matrix, from which we can calculate reduced density matrix. And in fact, this is the very simplest case in the case of as a test for a pure state and mixed state, which I am not discussing here, pure state and mixed state. So whether you know the complete knowledge of the subsystem or not gives you the answer, whether you have pure state or a mixed state. So this is, I'm not getting to that. Let me stop at this point itself. So you have a state and construct the density matrix by finding out the outer product, and you can trace out one of the subsystem. And in fact, this process is known as partial tracing. You can very well do it. It's a very well-known mathematical technique to find out the density matrix of the subsystem. It's known as reduced density matrix. I hope I'm clearing the point to Preeti, sorry.
Preeti, is it clear?
Yes, sir.
Right, thank you.
Thank you, sir.
Right. So what we have done, so let me recall what we are pursuing here. So we computed two things, retention fidelity and the deletion fidelity. You'd be asking why we have retention fidelity, because the very act of deleting one of the qubits affects the original qubit as well. That's why we are intent to calculate the retention, how much we are managed to maintain the input state. So that's why we have the retention fidelity, and of course deletion fidelity is also we want to find out. And this is the characteristic at various mission state, superposition state is also considered, and you can see the various characteristic at the so-called the superposition state. So this graph tells you the performance of the given deleting mission. So retention fidelity and the deletion fidelity help you to characterize the performance of a given deleting mission. So that is what is being done. And of course, if you ask me the question, what is the application? So note that we started off with something like a pure state, something like this. Let me consider this point, right? And what will happen after the action of deletion, we got into a entangled state. So the input state and the mission state becomes entangled. So question is, can we use that entanglement for anything? Yes, we can definitely we can characterize it using so-called the Bell's inequality. So there is a standard theorem which tells you that you can construct the row, which is nothing but the matrix, density matrix, using which you can construct a new matrix, 3 by 3 matrix in this case, and using this form where sigma I, sigma j are nothing but the well-known Pauli operators, and you can find out after constructing the matrix, you can find out the eigenvalues, and sum of two eigenvalues is denoted as m of rho. And usually you find out m of rho as less than 1. So it is the condition. This is the condition for a given state, and using which we can test what is the characteristic of our output state of deleting mission. So after the action of deletion, the input state and mission state becomes entangled, and what is the characteristic of it, that can be tested by calculating the Bell's inequality. So here you can see m of rho is computed. I have not shown the detailed calculation, which is a very elaborative one, and it is not possible to present over here. But the graphical view tells you that after constructing m via c, you can see the sum of two maximum eigenvalues is always less than 1, which indicates that the the output states of deleting mission do not violate Bell's inequality. And same is the case with respect to our deleting mission. This is in fact for the standard Pati-Bronstein, and the same is the case with our deleting mission. And the deleting output state can be used for the teleportation. So what is the teleportation? So let us consider two party, Alice and Bob, and they when they are together, they share an entangled pair, which we call it as EPR pair. That is nothing but the Bell state. Okay, let me write down that. So get 0, 0 plus get 1, 1. This is a typical entangled state, maximally entangled state. So Alice and Bob together, they generate this, and Alice is taking the first qubit with her, and Bob is taking the second qubit with him, and they are spatially separated. After some time, Alice wants to share the most general unknown qubit, single qubit, of course. Question is it possible for Alice and Bob to share this qubit, teleport this qubit, right? Most of the times when we say teleportation, people are under the impression that physically we are doing the teleportation. This sort of an image we arrived through so-called the Hollywood movies. It is not so. Rather we are transmitting the properties, the characteristic of the given state of the qubit, which is being teleported from one end to the other end. So it is indeed possible if Alice and Bob share an entangled pair, and so it can be done very nicely, and that is what we call it as quantum teleportation. And it is shown that when you have maximally entangled state like Bell state, then it is possible. So how it is done? You require one a EPR pair or Bell state plus classical communication. So what is classical communication? So making a phone call, sending an email, WhatsApp, all of them follow the so-called classical rule. So it is a classical communication. So the one Bell state plus one classical communication will help you to transmit the qubit. So it is possible. Now the question comes, what will happen if you have non-maximally entangled state? Can you still achieve teleportation? Answer to this question is also addressed. It is not possible. Deterministically, it is not possible. You have to have a probabilistic nature. So you can do so. You can transmit the qubit if you don't have maximally entangled state, but you have to compromise. So there is only the probabilistic of successful teleportation. So now we ask the question, what is the possibility of using the entangled state out of deleting operation for the teleportation channel? So there is a measure which we call Fmax, and it is computed for our deleting machine also. And the graph tells you that it is possible. All the outputs generated out of our deleting machine, of course, as well as Pati deleting machine, indeed is capable of using probabilistic teleportation. So we can use the output generated out of the deleting machine can be used for probabilistic teleportation. So though we started off the process of deletion with an intention to delete, we got into an entangled state. Now the entangled state can be used for the probabilistic teleportation process. And so these are some of the observations. The first and foremost, Pati deleting machine and our deleting machine are state dependent, input state dependent. And this is the characteristic. This is the characteristic of both Pati Bronstein deleting machine as well as the deleting machine proposed by us. And what are the characteristics we observed for Pati Bronstein? It is also observed for our deleting machine. And this gives us the most general statement that it is indeed possible to construct very many equivalent deleting machines, though the operations are fundamentally different. Pati Bronstein deleting machine and our deleting machine are fundamentally different, but the characteristics are indeed the same. Starting from retention fidelity, deletion fidelity, and whether it is useful for teleportation or not, all these characteristics are very much same for the Pati Bronstein as well as our deleting machine. So this gives us the confidence to come up with very many equivalent deleting machines, and one can understand the possibility of deleting further, or we can go for increasing the output state in terms of entanglement. Right. So having done this part, the very general question is, what about concatenating? So having learned that it is not possible to delete the state perfectly, is it possible to delete fidelity can be increased by adding one more deleting machine? So that is nothing but concatenation. So this idea is not very new to us. Even in the classical computation, we do this. So we add 2 or 3 NAND gates to construct the another operation. So similarly, we try here, which is nothing but concatenation of a Pati Bronstein and another Pati Bronstein. So you start off with the input state and feed to the Pati Bronstein and get the output. That output is given to another Pati Bronstein as an input and understand the characteristic. And so in terms of very definition, in terms of orthogonal states, the operation of concatenated deleting machine is given over here. But very strange point is that the retention fidelity, deletion fidelity, Fmax, all are all same. Whether you add one more deleting machine or one more deleting machine or one more deleting machine, it is going to be the same. So whatever retention fidelity, whatever deletion fidelity you're going to achieve with that of one deleting machine, that can be also achieved with 2. So it means it is suffice to have one deleting machine to generate the required entangled state out of the suitable input state. Because suitable input state is important. It is state dependent, input state dependent machines. So if I choose suitable input state, accordingly I can get the output state as per the operation of our deleting machine. Right. So same analysis is performed for our deleting machine as well, and we got into the same result. So once again, our understanding of equivalent deleting machine is enhanced. So Pati Bronstein and our deleting machine, the characteristics are the same. And not only that, when you concatenate Pati Bronstein with Pati Bronstein and the deleting machine of ours, and once again the same. So the concatenation characteristics also the same. So our intention of having concatenation help us to understand how much entangled state we can generate with one operation or 2 operation or 3 operation. Now it is very clear that it is enough to have one deleting operation by means of which we can achieve the required deleting operation, and hence we can generate the suitable entangled state. Right. The most general aspect is quantum correlation. Entanglement is one aspect, but the most general aspect is quantum correlations. And quantum correlations can be studied using very many interesting measure. One standard measure is negativity. Of course, one can also perform the calculation for discard, geometric discard and all. And it is very laborious, of course. And hence we take up the notion of negativity. And negativity is also a very standard way of calculating the quantum correlation. Right. In a bipartite state, negativity is defined something like the sum of negative eigenvalues. So we can consider this. We can find out the eigenvalues mod of sum, and we can get the measure of negativity. And we have this notion, namely, once again, we calculate the negativity created by quantum correlations measured by negativity. We want to understand, and hence we perform this. So we measure the negativity of one deleting mission, and we also perform the negativity of another deleting mission. You can see here alpha and alpha prime. These two are different because of the fact that it is a state dependent, input state dependent deleting mission. The sum of two will always be greater than the concatenated deleting mission. So this is a kind of a trivial one, nothing great about it, and the analysis also reveals the fact. But what is more important is this one, cloning and deleting. So we try to perform a cloning operation, then followed by a deleting operation. This has been studied very nicely in the literature. So Bazak and Hillary cloning mission is a well-known cloning mission, probabilistic cloning mission. And we try to copy the state. Clone the state probabilistically, and the output of which is given to Pati-Bronstein. And we analyze the output state. One can measure the retention fidelity, one can measure the deletion fidelity, whether the entangled state is maximally or not, whether it can be used for teleportation or not. All those questions can be analyzed, but most interesting analysis is this one. So what is this? This is nothing but a quantum correlation in general. It is the most general statement. It is applicable for negativity. It is applicable for quantum discard. It is applicable for geometric discard, and so on. So what is this? Basically, we have Bazak-Hillary cloning mission. So this is the final state. This is the input state. Input state is a product state. So it basically no correlation at all. So it is 0. So we have this, and output state is given to input of Pati-Bronstein, and hence we have, and finally we have this expression. So what is this expression? So this is nothing but quantum correlation measured by any measure like negativity discard geometry, and this is of cloning mission, and this is for deleting mission. When you do so, we got into a bound. This is the bound. So this bound tells you very interesting fact. The interesting fact is something like this. So this is the next slide. So the maximum value of negativity in this case is half, and this is nothing but cloning. So cloning plus deletion is always bound by this, right? More you try to copy, less you delete. So better we clone, worse we delete. So this is in terms of quantum correlation, we come into this picture. And it is speculated that this is also true for retention fidelity and the deletion fidelity. So it is speculated, it is not yet completely confirmed, and there are some violation also. So, but with respect to quantum correlation, one can straightforward way, we can say that more we clone, less we delete, and vice versa. And this is nothing but so-called the complementarity principle, and it is believed to be satisfied in terms of retention fidelity as well as deletion fidelity, which is yet to confirmed. So the complementarity principle come into picture so nicely in the case of concatenation of cloning and deletion. Cloning and deletion will give you this sort of a complementary nature. This is further investigation is very much required. And then because of this notion, so-called no cloning and no deletion, we have very fundamental question why it is so. Of course, we ascertain the reason, namely superposition principle, linearity, unitarity nature, all of them are come into picture, which prohibits a system from cloning perfectly, deleting the qubits perfectly. So what is the consequence? So it is known that entanglement cannot be increased by local operation and classical communication. This is a very strong theorem which cannot be violated at any level. So this is indeed proved at various points experimentally also, and it is a very strong theorem. It's a very strong theorem which cannot be violated. So now what would be the case here? If you have a deleting process, then you meaning to say, if deletion is possible, then you can decrease the entanglement by local operation and classical communication. So this is the clear-cut violation of the fundamental principle of entanglement. So which is very well confirmed now. So if at all you have a deleting machine, that will lead to the contradiction of fundamental aspect of entanglement, no change in entanglement under local operation and classical communication. Same thing holds good for no cloning as well. So if you able to clone, then you can increase the entanglement by local operation and classical communication. Once again, it is the sheer violation. So both these three, both local no cloning and no deleting theorem indicates, if at all you want to restore this fundamental theorem, you have to agree upon that no cloning is indeed the fundamental principle and no deletion is indeed the fundamental principle. So we have this notion, no deletion and no cloning principle follows from conservation of information. So if you able to increase entanglement or decrease entanglement by local operation, then something is going on, something strange is going on. What is that strange? There are many implications are being discussed in the literature. One thing is that, especially in the case of no cloning principle, if you perform cloning, then you can have superluminal signal. Meaning to say, you can send the signal faster than the speed of light. So that is not possible. So no cloning principle, no deleting principle impose a very fundamental restriction, and it is in accordance with LOCC, local operation and classical communication of entanglement. So it allows us to understand the physical reason for perfect deleting and cloning. Why it is impossible, that we understand. And you would be wondering why we say it's a conservation of information. See, when you have the process of deleting, so deletion can also be understood in a different style. So I have get psi, and let me have another get psi, and this is blank state. So I want to get rid of this. So there is an operation known as swap. I have an operation known as swap, which swap the input states. For example, you have 1 0 means then it will swap to 0 1 and vice versa. So what I can do, I can very well apply the swap operation. By doing so, I can apply the swap operation here. By doing so, I will get the input state and I will get 0 and get psi. What I can do, I can trace out this. I can trace out the subsystem. So meaning to say, I'm not really deleting, rather I'm taking away the state to somewhere else in the space, right? So somewhere else this information exists in nature. So that's why the swap operation is not considered. It is not, exchanging of qubits is not considered as a deletion. So the information already exists and you have moved from this point to other point by the action of swap. So philosophically speaking, whatever we have, whatever information we get, it is already exist in nature and we are observing now. And when we try to delete, we are not able to delete, rather we are moving the information from one end to the other end. That is what the so-called the notion of conservation of quantum information. So it should be understood this way only. So deleting process, it is not possible, and hence this indicates that it is not possible to increase the entanglement, rather decrease the entanglement. Same is the case with that of cloning also. So there is a point which tells you that entanglement can be neither increased nor decreased under local operation and classical communication. So if at all you want to get hold of this strong fundamental rule of entanglement under LOCC, you have to agree upon no deletion and no cloning. And having said this, what is the application? What is the application? Then why do we require? So if you are not able to have cloning and deleting in the quantum computer, if at all you have a quantum computer, then what is the advantage? Still people say it is advantage because you can still perform cloning and deleting in a probabilistic way, in a very probabilistic way. So it is an input state dependent, and tune your input state accordingly. You can have the maximized way of deleting fidelity and the retention fidelity, right? So this notion is still under many debate in the sense that people are not convinced, and why we have a half-baked idea, and it is, of course, it is in accordance with our understanding, but conceiving this notion, conservation of information, still it is under consideration for very many point of view. So analysis of conservation of quantum information still open problem, and understanding of conservation of quantum information from thermodynamics point of view is yet another open aspect which I have not covered here. So from thermodynamic point of view also it is interesting, because if you classically if you want to erase, right, delete it, you can do at the cost of spending some energy. It is of course irreversible. It is irreversible, right, in the case of classical notion. But so in terms of concept of entropy, you can also speak. Okay, entropy can only increase and it cannot be decreased. So all those notion can also be come into picture when you talk about the quantum information, and from thermodynamics point of view, in particular the second law of thermodynamics point of view also, one can think of quantum information, right? So as of now we understand one thing for sure: we cannot cut, we cannot copy, and hence we cannot paste. That is for sure. Definitely we can't do this in a very deterministic way as we practice in the classical computation. But we can do it in a probabilistic way. And these three principles, of course, in general, no-go theorem, say something more than what we anticipate in the name of conservation of quantum information. So this is what people speculate, and we have to go further along in the road to come up with a very clear-cut notion from thermodynamics point of view, also from information point of view also. Right. So these are some of the reference, and so I stop here. I think I'm on time. Right. So I wish to have a discussion with you.
Yeah. Thank you, Balakrishnan.
Yes.
Thank you. So this forum is open for questions, clarifications, doubts. Students, you can raise your doubts, or you can write your doubts in the chat box. I think I'm not getting. Balakrishnan, I have a couple of questions.
Yes, please.
You said linearity prohibits no cloning theory, right?
Yeah.
Can you explain how
Yeah.
it prohibits?
Right. So as I mentioned here, right, as I mentioned in the presentation, so you have get psi, and it's a general state. Let me take a general state here. A get 0 plus B get 1. Right. So this is the state I want to copy. So this is my blank sheet, right? Something like a white sheet in a copying machine where I want to copy the content. So my input state is something like A0 plus B1, and this the blank state. So I have A00 plus B10. Right. So now what I want to have, what I anticipate, if at all I have a deleting proper, rather cloning machine, what it supposed to do, it's supposed to have get psi and get psi. So this is what I want to have. So this is 0. In fact, sorry, this is 0. After the action of cloning, I am supposed to have this state. This is what I expect. This is what I expect. So now what happens if I do so, if I open up this, if I take the tensor product, I will get something like a square 0 0 plus b square 1 1 plus a b 0 1 plus 1 0. I'm just write down in a shortcut way. And this is the state. So this is what we have after this operation. But what we want, we want this, but what we get is something like this. See, where we have the so-called as a C0 operation. When C0 operation is allowed on this, after all, I will get A00 because the very operational definition of C0 is something like this. Whenever the first qubit is 0, the second qubit is left out as such. And whenever the operation of C0 acting on first qubit maximum, then it will be flipped. It is 1 0 becomes 1 1. Right. So this is what we are getting. So we are supposed to have this. And what we are having here after the action of well-known C0 is this.
Yeah.
So if I want to have this condition to be satisfied, I have to kill this term.
Yes.
Right. So AB has to be killed. So either A has to be 0 or B has to be 0. So if I say A is 0, then I will fall back. If you look at this, the most general state, if A is 0, then I will have the well-known state. So it becomes a known state. So the known state can be done anything we want. Okay, but unknown state cannot be done.
Yeah. So the entanglement automatically enters into this.
Correct, exactly.
Okay. Thank you. So there one more general question.
Yeah.
So people are talking about non-Hermitian systems, PT-centric systems, and other things. So whether your findings can be also be extended to those kind of systems.
Right, sir, exactly. So as a matter of fact, we are saying cloning and deleting, right? So it is not time reversal. That is the first interesting aspect.
Okay.
It is not time reversal. One can also analyze from that point of view. As I mentioned, we don't know what is the reverse process of cloning. Though in a very superficial ways, we can say copy is the inverse of deletion, and deletion inverse of copying, but fundamentally it is not in the domain of quantum mechanics. So the very first reason people ascertain is it is not time reversal. These two are not time reversal. And one can analyze from that point of view also. Yes.
So students, do you have some clarifications, doubts?
Sir?
Yes, please.
Sir, actually in negativity, you find the negative eigenvalues of density matrix, right?
Correct.
Sir, so the density matrix property is, it should be semi-definite.
Right.
So the eigenvalue should also be positive.
True.
So how do you find this negative eigenvalues of the density matrix?
Right. See, understand. Here we do have negative eigenvalues, of course, because of the bipartite nature. You are absolutely correct. But this is negativity in general, we defined in this fashion. Okay. And as you rightly said, we will get only positive eigenvalues. You're right. Absolutely right. I'm just writing down the very definition of negativity. That's it.
Oh, okay. Thank you.
Let me see. You have any other question, doubts?
And of course, I guess I'm little fast, and I try to
No.
cover with the content what I want to deliver. So meaning very simple. Two things take home lesson for the students especially. So quantum computer, indeed, it's going to be very strange because we are not going to have cut, copy, paste. That is one thing. But more profound point of view is that conservation laws or the very fundamental nature always follow some sort of a conservation rule. And people who are working in quantum information theory and computation also try to find out the underlying conservation rule. And that's how we got into the notion of no-go theorems, though it looks kind of restriction or constraint in comparison with classical computation. But we look at in a different way because we want to understand the nature, and is in the form of a conservation rule, and that can be hopefully will be analyzed via the no-go theorems.
Yeah. Students, are there further questions?
Sir, can you explain more about this quantum discord?
Quantum discard, okay, very good. Quantum discard is something like this. Right. See, right. So quantum discard tells you what is left out as a quantum correlation. What is left out as a quantum correlation? So you have a system, okay, bipartite system, and you find out how much the quantum correlation can be arrived by means of finding out something like rho AB minus rho A. There is a measure here, okay, which I'm not writing. Okay, so you are discard all the classical measures, classical notions. Then what you left out is nothing but the discard. Okay, since I'm not working exactly, I don't know the proper definition in terms of expression. But of course, quantum discard is the alternate for negativity. But negativity can be measured quite easily.
Okay.
Yeah. Thank you.
Students. All right, Balakrishnan. We are not getting, we are not receiving more questions. Maybe they will write to you.
Right. Thank you.
So since there are no more questions, I would like to conclude the session by thanking Dr. Balakrishnan for accepting our invitation and giving a very wonderful talk on no-go theorem. Today we understood what is no-go theorem and its implications and applications as well. Thank you, Balakrishnan.
Thanks a lot, sir. Thanks for giving the opportunity. Thank you.